Hello and welcome to today's lesson on stretching springs. Our learning objectives are to explain how we stretch, bend or compress an object, to describe the difference between elastic and plastic deformation caused by stretching forces, describe the relationship between a force and an extension for a spring, and calculate the spring constant. But before we start on the springs, have a look at this graph. A common exam question is asking students to describe the graph. So have a think about how you would describe this graph. Pause the video if you'd like for a couple of minutes while you think about what you'd give for your description. Quite a common answer is for students to write something like "it goes up." This answer won't get you very many marks in the exam, and we're going to look at a far better answer. You could say something like, "as the number of pizzas goes up, the number of tomatoes goes up." Or even better, the number of pizzas and the number of tomatoes is directly proportional. Being able to identify a directly proportional graph is quite an important skill in science. Here we have 4 graphs. I'd like you to have a look at those and identify which of these 4 graphs you would describe as being directly proportional. For a graph to be directly proportional, it should go through the origin and have a constant positive gradient. Graph A shows a directly proportional relationship. As the value on the x-axis doubles, the value on the y-axis would also double. Let's move on to bending and stretching objects. If a bouncing ball was to hit the floor, it would deform and change its shape. If 2 forces act on an object, they can put it in compression, squashing it, or if they act in the opposite direction, they can put it under tension, stretching it out. 3 forces can create a bending force on the object. There are also torsion and shear forces, although these last 2 are outside the scope of the GCSE, and it is just compressive, tension and bending forces that we need to focus on. Some objects, when they are stretched by a force, will not return to their original shape. We call these types of materials plastic. In this case, we're talking about plastic deformation, in that the material will undergo plastic deformation and stay deformed after a force is exerted on it which bends it out of shape, rather than springing back like an elastic material would do. It is not the same thing as being made out of plastic in a chemical sense. Materials that undergo plastic deformation do not return to their original shape when the force is removed. Many modern fabrics are made out of elastic materials which spring back to their original shape when the force is removed. Chewy sweets, when you squash them, will get plastically deformed and stay in their new shape. In contrast, wine gums, if you squash them gently, will spring back to their original shape when the force is removed. Does a rubber band deform plastically or elastically when placed under a force? The answer is it deforms elastically because it springs back to its original shape when the force is removed. Does Play-Doh deform plastically or elastically under a force? Play-Doh undergoes plastic deformation, retaining its new shape even when the force is removed. What about a bungee cord? Would this be plastic or elastic deformation? Bungee cords are elastic. What about stretchy sportswear such as Lycra? Is that plastic or elastic deformation? Lycra does spring back to its original shape, so it is elastic. Does metal deform plastically or elastically when placed under a force? I would normally say it undergoes plastic deformation and adopts the new shape after the force is removed, but there is a small region where if a small force is applied, then you will get some elastic deformation and the metal can spring back to its original shape. Finally, is Stretch Armstrong elastic or plastic? He is, of course, elastic, returning to his original shape no matter how big a force you apply, so long as you don't break him. Right, can I ask you now to pause the video and write a definition in your book for elastic and plastic? If you're not sure what to write, then there are definitions in the back of your textbook or electronic book. Robert Hooke was a contemporary of Sir Isaac Newton, and he came up with many great discoveries in the field of physics, one of which was the relationship between springs and their extension when they're placed under a force. Hooke recognised that if you put a small mass on a spring, it would extend, in this case by 2 centimetres. If you doubled the mass, the extension would double, in this case to 4 centimetres. 3 times the mass and you would have 3 times the extension, 4 times the mass and 4 times the extension. This graph shows the extension of a spring as it varies with force. As you can tell from the shape of the graph, force and extension are directly proportional to each other for this spring. So to summarise Hooke's law, Hooke recognised that the force and extension are directly proportional for a spring, and if the force is doubled, the extension would be doubled. Elastic materials do usually have a limit though, called the elastic limit, after which they stop behaving elastically and behave plastically, deforming permanently. If you stretch a spring too far, then it will not go back to its original shape. Here you can see a graph with the elastic region, which is a linear region, showing a directly proportional relationship between the force and the extension, and then there is an elastic limit, after which the object stops behaving elastically. So objects which obey Hooke's law will have a linear region where the force is proportional to the extension. Some objects and materials don't have a linear region at all, such as rubber. Hooke's law has an equation associated with it, and you do need to recall and apply this equation. The equation is force equals spring constant times extension. Force is measured in newtons, spring constant is measured in newtons per metre, and extension is measured in metres. Pause the video here and copy this equation into your books. In this equation, K is known as the spring constant, which is a measurement of how stiff the material is. You can find the spring constant by taking the gradient of a force extension graph. The units for the spring constant are newtons per metre. And the higher the value for K, the stiffer the spring is. Any material with a high value of K will need a larger force to get a given extension. If you need to rearrange the equation, you can use this formula triangle, FKX. Pause the video now while you copy this into your books. To find the spring constant, we need to find the gradient of the graph, which means drawing a large triangle under the graph. Here, the increase in force is 70 newtons for our triangle, and the increase in the extension is 0.7 meters. By dividing force by extension, we find the spring constant has a value of 100 newtons per meter. Don't forget you always need to change your extensions into meters first before doing your calculations. Find the force required to stretch a spring with a spring constant of 20 newtons per meter so that it extends by half a meter. Write this answer in your book and pause the video now while you work it out. You should have got an answer of 10 newtons. Find the force required to stretch a spring with a spring constant of 100 newtons per meter so that it extends by 4 centimeters. Again, pause the video and write the answer in your book. Don't forget to show you're working out, and watch out because the extension is in centimeters. You need to change it into meters first. You should have found the answer was 4 newtons. This time you're finding the spring constant of a spring which extends by 6 centimeters when a force of 3 newtons is applied to it. Once again, pause the video and write your answer, showing you're working out in your book. And the spring constant would be 50 newtons per meter. A spring with a spring constant of 100 newtons per meter is loaded with a force of 8 newtons, By how much will it extend? Pause the video and write the full answer in your books. It would extend by 0.08 meters or 8 centimeters. Find the spring constant of a spring that extends by 8 centimeters when a force of 2 newtons is applied to it. Pause the video here and write the answer in your book. The answer would be 25 newtons per meter. Here we have two spring systems. On the left hand side you have a single spring with a mass hanging from it, and on the right hand side two identical springs, again with the same mass hanging from them. How would the stiffness of the two springs compare with the stiffness of the single spring? Well, the extension of the two springs in series would be twice as large, and therefore the stiffness would be half as much. Now we have two springs in parallel. How would their stiffness compare with the stiffness of the original single spring and mass system? Well, in this case, each spring is only having to support half of the mass, and therefore they will only extend by half as much, so they will be twice as stiff. Right, well that brings us to the end of today's lesson. I hope you found it useful, and thank you very much.